Welcome everyone to the SPREE seminar. It's my pleasure to introduce James Hazelton, who is just about to complete his PhD on risks and benefits for PV hybrid mini-grid systems. And I'm particularly pleased because he'll be my first PhD student to complete. So James's work's really of significant interest to the industry as well as academia because of the role that renewable energy mini-grids are expected to play in terms of meeting energy access targets around the world. So James has some really interesting insights for us, particularly in terms of the modelling and performance monitoring of these types of systems and how that can better inform our understanding of the risks. So thanks very much, James.
Thanks, Anna. So this catchy title, Reducing Risks and Maximising Benefits for PV Hybrid Mini-Grid Systems, Lessons from the Asia Pacific, is the title of my thesis, as you might have guessed. I'm going to launch straight into the outline because we've got a fair bit to get through. I'm going to start off with a couple of definitions of often ill-defined terms. One is mini-grid and the other one is risks. Talk about a little bit about the global context and the problem statement regarding my research and what the thesis was trying to tackle. The method and framework for doing so that I developed, the case studies, which is Northern Territory, Australia and Malaysian Borneo, some recommendations about how we can do things a little bit better, and then finally the conclusion. So beginning with mini-grid, and this term is often used in conjunction with microgrid, picogrid, nanogrid. It all depends on where you stand in the electricity industry. My definition that I use is a standalone power network that manages energy supply and demand. This is a pretty classical case for my research. We've got a community of households, residential users, being connected to a system that composes of a diesel generator set, PV array being solar, a battery system, and this conjunction forms a hybrid system. So the scope of my research was essentially a PV hybrid, which includes PV in combination with other generation sources. Importantly, as opposed to some other mini-grids, sometimes university campuses are called microgrids or mini-grids, but they're also connected to a centralised grid. These are very much standalone systems because we're targeting multi-user rural electrification. So those systems that are very much isolated from existing electricity infrastructure, whether it's because they're on an island or because they're in the very centre of Australia. In my case, I'm going to talk about both a retrofit to existing diesel. So that is an operating diesel mini-grid that's currently going to be introduced with solar, so a retrofit of solar into that diesel system, as well as greenfield sites. And greenfield refers to times when there's no electricity infrastructure there in place and this system's gone in to provide energy access. It's useful sometimes for people to consider the sizes of these things. In yellow there I've put village mini-grids and island mini-grids just in terms of arbitrary kind of generic sizes, but relative to the other energy access options. So solar lanterns, DC home systems, AC-DC home systems such as what we get in Sydney, all fit on this scale. Mini-grids are very much on the scale for me. I talk about systems between 5 kilowatts all the way through to 3 megawatts. So that's a really broad scope, and this is part of the reason why they're often ill-defined. When you cover that scale, you're obviously talking about multiple users. In some cases, it might just be a mine site that you're serving, but this is outside the scope of my research. And you also get into this interesting area around how you actually implement the project, because you're not quite at the level that can be financed with conventional energy project finance. And you're also dabbling in the world of development, international development in terms of programs for rural electrification. So because of that, you end up with all these different ownership types that might be possible in a mini-grid system, including utility-based systems such as what happens in Northern Territory with Power and Water Corporation, community ownership, where a community puts together their resources to build a mini-grid, as well as private ownerships and any combination or hybrid of these approaches as well. The picture tells 1,000 words, and it's maybe useful to introduce firstly what I'm going to be talking about. At the top there, this is a system providing new energy access in Borneo. This is 1.1 megawatts of solar connected to a standalone mini-grid system. In the tall hut there is 5 diesel generators between 400 and 200 kilowatts each. They'll run individually rather than simultaneously. On the right of that tall hut is a large battery room with 3 megawatt hours of installed capacity. and on the left you'll see the diesel fuel tanks as well. Additional to this site down the road is another older site that they had that was connecting a smaller amount of users, which was another PV system which now operates as essentially an AC coupled grid connected system. So no different from the grid connected system in Australia, that's just a smaller contribution into this larger scale system that's forming the grid. In the bottom we've got Northern Territory, Australia. This is a site called Kalkarinji, which is about 500 kilometres northwest of Alice Springs. This was an existing diesel site that had solar power installed on it. This is 402 kilowatts of solar, a small battery system, which is the white container that you can just make out at the back of the system to basically act as grid stability storage. So large-scale PV fluctuations are smoothed out by these sealed lead-acid batteries that exist in the container. And most of the hard lifting in this system is done by the diesel generators, which are in the green shed there. You can also make out the 3 feeders, which go out to different Aboriginal communities and the public townships as well. So the other badly defined term which I've got to start with is risk. In a very basic sense, it's the undesirable implication of uncertainty, which was defined by Chapman and Cooper in 1982. A lot of risk work stems out of project management work that happened in the 80s and 90s. For this research, I'm going to use the term uncertainty that impacts outcomes in a positive and negative way, so introduce some tangibility in terms of project outcomes. Importantly, its consideration is vital in terms of any decision making. When Ziv asked me to do a seminar, I thought it was pretty likely that I'd be overseas by this stage, so I said, yeah, no worries, mate. And now I'm actually leaving tomorrow, so just missed out. So I took that risk and I lost, but here I am. Risk evaluation can fall into classical or conceptual models. What I mean by classical is more quantitative approaches. So if you're similar to what Rhett was talking about when he did his seminar, if you're on a manufacturing line where you've got heaps of data, you can more accurately assess and quantify the risks that are involved. But also conceptual models, on the other hand, which is what we probably think about when we do a risk assessment, those probability and impact curves that we see, that's very much a conceptual model. The origination of that was actually Pascal, the French philosopher, physicist, mathematician, who basically decided halfway through his life that he was going to be a Christian because although it was unlikely that God existed, the consequence of God existing and he wasn't acting like a good Christian was so large in that he'd go to hell that it was worth becoming a Christian. So that was the first ever risk assessment, well, one of the formative probability and risk assessments of the time. Of course, it depends on where you stand when you're viewing a project or a decision. It accrues to the different parties and these can be just perceived differently. Importantly, if anyone's ever done a study onto barriers for renewable energy technology, the perceptions may not align with reality. So one of the often cited barriers for renewable energy is that people perceive it to be very risky when in actual fact it may not be the case. So putting these two things together, I like to start to get people's understanding about it. Start with a project development case, which most people are aware of, that when you are trying to finance a project, and this comes from RETScreen, a micro hydro project, when you first start estimating costs, you have a large degree of uncertainty. And this scale they're using accuracy, but what this is essentially a representation of uncertainty. And as you get closer to project feasibility studies, tenders and then construction, your degree of uncertainty gets narrower and narrower until you arrive at the final cost for the system. Now this could be cost, this could be time blowouts, this could be anything you want to talk about in terms of performance. It's useful to consider the whole project timeline that we typically use for a renewable energy project, from proposal, detailed feasibility study, design, construction, commissioning, and then while it's just a small box here, operation as well, which is, I spend a lot of my time looking at the operation of renewable energy assets. So I like to put this on a time scale and say, well, operation is actually 20 years, all this other stuff happens over 2 years. So while this is only a small box, it actually has the proof of the pudding in terms of what services are going to be delivered. So putting that to one side, and we'll be generous here and give the developers half, and then the operators will get the other half. There's uncertainty in project development, and then there's uncertainty in operation and service delivery. So when you have finally built that project, the question then we have to ask is it performing as expected? How are we measuring that performance? And how do we avoid, reduce, transfer or retain the risks that are involved in working through this project? So I kind of flip that diagram on its side and say, well, all right, if we have cumulative performance over the lifetime of a project over 20 years, you can have outperformance and underperformance, and as the project proceeds, you might operate within certain bands of this uncertainty. So this is very much conceptual. I'll come back to this at the end to describe a little bit more about it. What is really important for renewable energy projects is, and I'm just talking about a mini-grid project here at the start, but this is true for all renewable energy projects. If we have two systems with the same levelized cost of electricity, this is a net cash flow diagram of a 100% diesel system versus below I'll put a medium or high penetration renewable energy scenario as well. This is the cash flow over time. I've deliberately kept this pretty scant of details because what I want you to focus on is the shape of these profiles. Obviously, operation over time is pretty consistent and the operational costs are very consistent over a diesel system, but with renewable energy you have a lot of debt or capital that's needed up front, and then that you obviously make that back with lower operating expenses over the lifetime of the project. So that's the difference in the two shapes here. What is often, well, not negated, but what people don't often think about is year 20 is a long way away. So what might happen, and this is the case for mini-grids especially, they face these risks that, well, you've built a mini-grid, but then the regular grid comes and interrupts what the business model and the original business case was when we made this decision to choose renewable energy. Similarly, you could have more consequential stuff like an earthquake that knocks out the mini-grid. So if you take away, due to whatever reason, failure or better options are available, your customer base has moved, then suddenly the levelized cost of electricity between these two options has gone up dramatically in the bottom case and is much reduced in the lower case. Or sorry, it's still gone up, but relatively speaking, the renewable energy case is much higher. So the core point of this is that renewable energy faces a lot more risk because it's capital intensive at the start. And in doing that, and in being that way, it will always be viewed as a little bit more risky. Onto energy access, and it's been well established that energy plays a crucial role in improving lives and reducing poverty. There's currently the UN-sanctioned Sustainable Energy for All initiative, which is aiming for universal energy access by 2030. Within that framework, mini-grids are identified as a high impact opportunity. They view this as something that can really bring energy access to a lot more people than what's been done by conventional electricity. And the IEA's forecast for achieving this in their least cost scenario was through a combination of on-grid, mini-grids and standalone systems, standalone referring to solar home systems or personal diesel gensets, etc. So mini-grids are forecast to have a bit of an impact in the future. This is between the years 2010, 2030, contribution to new energy access in each of the countries, or each of the regions, I should say. In terms of reaching this at the moment, attracting the finance to achieve it is well below par at the moment. So at the top there, in this bar chart, we've got the current situation, how much funding is going into energy access per year. What we'd expect if we continue, well, the new policy scenario out to 2030 in terms of a business as usual case, as well as the universal access scenario, which is what we can actually achieve, what we actually need to achieve the goals. This might seem incredibly ambitious, but when you consider that $37 billion a year is spent on kerosene and biomass products used for simple heating and simple lighting, there's actually a whole lot of opportunity here to provide these systems with renewable energy or mini-grid systems. So it's more about changing the way that we're currently doing systems from an on-grid extension scenario into making it more compelling to have mini-grids and off-grid products. So a little bit more detail into that light blue section of the curve, which is the multilateral development banks and the bilateral development banks. This is each bank's performance in terms of where they're spending their money, or what they're investing in, I should say. What's needed there is shown on the right, and where each of them are in terms of underperforming. And this is from a report by the Sierra Club titled "Still Failing to Solve Energy Poverty," and it gives them an F based on they can't deliver what they've been targeting to do. So onto the problem statement. Still 1.2 billion unelectrified users, 2.7 billion using traditional biomass. Conventional approaches will fall short of the targets for sustainable energy for all. Obviously, alternative approaches will be necessary. While renewable energy is pretty much now conventional technology, it's very popular in a lot of developed and developing countries, it's still considered risky just because of the issues that I described earlier. The investment of such needs to be more attractive. Often, and we heard this last week at the Clean Energy Investment Forum, the money's available, we just need bankable projects. And also, you know, the bank saying that we've got pilot fatigue and that there's been so many pilot projects done, but no one's actually demonstrated a model that truly works. So these things are sort of coming together in terms of the challenges that we have in terms of demonstrating mini-grids and renewable energy mini-grids to work. There's also the risk that what happened with solar home systems where quality was poor, where the end users won't want these things. They'll still demand the grid and they'll, you know, refuse to pay for something that is substandard in their view. But mini-grids kind of stems that bridge between small-scale distributed systems and on-grid systems and provides surplus electricity to the end user, which is what they prefer. From looking at this in a more academic sense, there's a lot of literature on hybrid mini-grid modelling, but there's actually a real shortage of operational experience that can be used to verify the models and to guide the decision making. So I arrive at my research question in terms of how can we better model and manage the risks involved in PV mini-grid deployment in the Asia Pacific. So the aim pretty much reflects that research statement. I'm consisting of 4 objectives here: identifying and describing the various risks and benefits in the deployment, investigate the cases that we found in the Asia Pacific, assessing the adequacy of those cases as well as the mini-grid modelling software and the performance measures that are used in each case, looking for opportunities to improve them, and then recommending ways to better manage the risk and the uncertainty in the existing programs as well as expected future project development. So while you might recognise this from Oliver Twist's 1948 film, this was actually me begging for data in 2012. You'll notice the youthful appearance and full head of hair representative of the taxing nature of this task. But this was essentially how I started out, looking for data on these systems to begin with, approaching countless blind emails, blind calls to just case studies that I'd read about. It was pretty obvious that we needed a case study approach. There's a lot of factors that go into rural electrification, so that's where we arrived. Ended up with Northern Territory Australia on the books and Sabah. This is Sabah's in Eastern Malaysia. I'll come to that in a second, but this was the sort of data fields that I was getting. From Northern Territory, we got 1 year of data from one site. This is 10-minute operational data. Kalkarinji, 10-minute operational data for the next year. And then in Sabah, a little bit smaller, but 1 minute data on their hybrid systems as well. Talk to that in a bit more detail. Did a literature review to start with, multi-stakeholder interviews from all over all the related people. If we come back to that diagram I showed you at the start, trying to capture all of the perceptions around risk. Using that to describe the deployment. In red here, I've got all the outcomes that kind of came from each one of these things. Field visits were conducted in 2014, 2015, and yeah, not so much in 2013. I was still begging for data back then. Data collection itself was challenging, and I'll come to that. And then end user surveys as well. So most importantly at the end of the day is to talk to the end user about the service delivery they're getting, how much they're spending on electricity, etc. So this was a whole journal paper, but I've summarised it into one chart. We kind of categorised what are some of the risks that come up in mini-grids, and I'll just maybe talk to 2 or 3 of these. Load uncertainty was the big one in terms of a performance risk. That relates to the fact that when you're trying to design a standalone system, you're very much trying to custom fit an energy system to a particular demand. The first problem with that is that demand is a relative unknown, but it's also a moving target. So population growth, livelihoods, people's living, how much money they have to spend on appliances, etc., all relate to that. So if you're talking about over 20 years, you can have significant change in terms of demand. And you know, utilities and the AEMC here in Australia have enough trouble forecasting demand in large-scale systems where there's a lot more diversification. You have the same challenges in microgrids, except there's diseconomies of scale in terms of doing it all over the place. On the commercial front, this relates to non-technical risks which influence the financial viability. There's been reference to inadequate business structures, so finding the right model. Stakeholder management, equipment supply issues, we'll come to a few of these in time. And then finally, in the programmatic sense, this is the legal, regulatory and political influences that influence these decisions, that will affect the decisions. Probably one of the main ones there is future connectivity. So if you've gone and invested in a mini-grid and then the utility extends the central grid into your location, you've essentially ruined the business model for the person that originally built that. Licensing is another issue. In a lot of countries in Africa, you can't charge more than what the utility will charge for electricity. So even though there might be a demand for energy and private partners can actually offer that electricity to them at a bit of a premium and make money out of it, it'll actually be against the law for them to do so. So there's a whole bunch of challenges that come up, or risks that come up in this. In putting those three sort of spheres of risk together, there's performance risk at the centre, commercial risk on the outer, and then programmatic risk. And what I do in my research is applying a lens of, and this is a traditional risk management approach, of identification, management, mitigation and monitoring to each one of those spheres. The reason they're positioned like that is that you can, there's certainly a degree of influence that comes between those, but you can also manage some of the risk by aggregating each one of your projects' performance risks within a commercial space by having more projects with different commercial partners, for instance. I'm not going to dwell too much more on that because we'll run out of time. So a bit more interesting now, we'll jump into the case studies. The Northern Territory, Australia, as most people here are probably aware, is one of our largest states, 240,000 people, population density of less than 0.2 people per square kilometre, so remoteness is a real issue out here. The state utility providers, Power and Water Corporation, they operate indigenous energy services, which is a not-for-profit subsidised by the federal and state governments. And they provide services essentially cross-subsidised. This includes water and electricity to 38,000 people living outside of Darwin, Katherine, Alice Springs. In providing those energy services, they have to rely a lot on mini-grids. Historically, that's been a lot of diesel, which we can see here. This is a map of all their sites. Because they're working across such a space, and obviously there's a lot of potential in the Northern Territory for solar, in 2011 there was a tender put out for a novel PPA arrangement. So this is a joint public-private partnership essentially between the utility and getting someone else in to bring in solar into these mini-grids. So the tender was won by Epuron. They originally had it technology agnostic so that you could propose any technology you wanted, but they chose flat plate PV because it's the most economic at the time. Importantly, they didn't choose much in terms of storage. They said we'd just reduce the storage because it's a very cost intensive component of these projects. So it's very much a medium to low penetration PV solution with small scale storage attached, I should say. This also coincided with some other works, including Power and Water put on a system at Lake Nash and put on a wind system at Lake Nash and upgrades to existing diesel generators. Here's what a configuration of the system would look like, both in terms of block diagram, electrically speaking, as well as the contractual arrangements. So on the left of each one of these sites, Tea Tree and Kalkarindji, we've got Power and Water Corporation with they own the diesel generators and they're responsible for the loads and the network that runs between them. On the other side of the coin is Epuron, and that dotted line there, Epuron have, first of all, AC coupled components of batteries and PV, and that dotted line essentially works as a PPA agreement where Power and Water will exchange cash for the kilowatt hours that Epuron sends across the line. This is what 7 days of operation looks like at both sites. You can see that Power and Water they'll operate their diesels in a non-simultaneous manner so that each one's operated, they size their generators first of all so that there's a few different sizes available and they pick the one that they want to run at that particular time. So across 7 days you see this profile where the yellow is contributing to the load, which is the dotted line, reducing the peak load during the daytimes. and the diesel generators will be scheduled up according to what the remaining load is in these systems. In terms of the results from this, PV generation was over, this is an annual energy target of, an annualised energy contribution of 18%. The maximum PV penetration was recorded at 77% and 96% at Kalkarinji. This is based on 10-minute instantaneous samples, so these figures aren't probably as accurate as what would have if we had bigger data sets, but that's one of the problems. At Kalkarinji, the fuel saving was a little bit lower due to the fact they had one of their generators out and was running a lot lower capacity for a lot of the time. They were running a large generator at lower capacity. So ASIM was developed as part of these projects. ASIM's meant to be complementary to the widely recognised Minigrid software Homer. It was developed as like an open source tool that Power and Water Corporation would use to help model their diesel systems and to better reflect the integration of PV into the control system. It basically allows custom time step analysis. So while Homer can go down to 1 minute and doesn't do diesel generator dispatch very well, this can go down to 1 second and can do it quite a bit more accurately. As I said, it's complementary to Homer. Anyone's welcome to access it and use it. What I used ASIM for was because, and this happens a lot in Minigrid projects, there was no data there before, or there's no operating data to compare it to. So when you want to talk about what are the results from integrating, what are the benefits and what are the risks in integrating PV, we couldn't really measure what was there beforehand. So I developed a reference case in ASIM and quite accurately modelled how the system would be performing. And then by tweaking some of these variables, I was able to take the solar back out and then look at quite accurately how the system would have run had there not been solar. And so this is useful firstly because the data set may not have been available, but also, as I mentioned before, demand's a bit of a moving target. So if you take demand out of the, or if you're trying to assess what demand is on a year-to-year basis, if you've got, spiralling load growth or things changing within your system, then it's not accurate to just say that, you can't compare 2013 to 2014. You have to do a bit more analysis. This is the results and how close we get the ASIM reference case versus the system without PV. So it's not too bad in terms of these measurements. This all kind of contributes to acknowledging some of the benefits and the risks that go in because, as I'm about to show, when you have PV penetration, this is from T-Tree, coming into the system, you're actually pushing that smaller diesel generator lower and lower on its operating curve. And diesel generators don't like that because they operate at a lower temperature when they're operating at a lower power output. And when you have a lower temperature, your combustion may not be complete. If the combustion's not complete, you have a build-up in the cylinder chamber. That can add to increased wear on the generators over time. So these sort of issues kind of need to be avoided. What we could do with ASIM, when the no PV case that I modelled before, is represent how the system operated beforehand. It's still not ideal, mind you. There's operation below 40%, but this is more typical of how a diesel generator supplier would say that you should operate your system. So the next thing to do then was to make the business case for introducing a smaller diesel generator system. This induced a further fuel saving of 1%. We've added a 320 kilowatt generator on top of that. And importantly, when we do this, we can actually get an even better operating curve profile. So in summary of findings on the performance risk side in the Northern Territory, I was a little bit surprised that the original diesel configuration was so suboptimal compared to what the load should be. You just expect that maybe they were done a little bit better, but it makes sense when you think about how demand changes. It's all the same issues that we have in renewable energy systems, in that you've only got so much inventory and you've got to get the best match between them, and whatever's there, if the load changes, it doesn't matter, we'll just leave whatever's there. The more penetration you put into these PV Minigrid systems, we've done quite a bit of work in terms of quantifying what those effects were, which obviously affects some of the risks. As the project manager at Power and Water pointed out, you can actually worsen this problem because quite conservative utility generator designers will factor in a substantial factor of safety when they're sizing the cooling fans for these generators, because this is really hot. T-Tree's just north of Alice Springs, so up to 50-degree days. what they'll tend to do is design the system to operate at full load on the hottest day of the year. So first of all, that's reasonable if you're talking about system reliability, but when the system was designed that way and then you're integrating the solar, you're actually exposing it to quite a lot more reduced temperature operation, and that kind of agitates these problems that we have in terms of lower operating ranges. There was a few issues in the control integration. The original designers underestimated the variability because they didn't have the right data available on the solar resource. As I showed in the block diagram earlier, at Kalkarinji, there was only 2 generators on site for a little while, but the system still delivered that electricity. So, I mean, having these 3 generators on site, there's a reason they have 3, is that if one fails, they can still service one and operate the other. But in terms of that, resiliency seemed to be adequate to cope. Yeah, we talked about some of the uncertainty around demands earlier. In these cases, there was a good data set beforehand, or there was a reasonable data set, I should say, beforehand about what these communities use, and there's not expected to be a great deal of change in terms of what the communities use. So in this case, we didn't really see much uncertainty around that, but there have been documented examples in the NT previously regarding the transience of like indigenous communities that might move on, or in the case of Parachilna, they'd upgraded to a solar diesel system in early 2000s. I can't remember the exact date, but just after they did that, the pub put in a backpackers and they put in a water treatment plant as well. So the original design load was changed dramatically, and that resulted in additional battery deratings, etc., or battery, what's the term? Depth of discharge, shall we say. In terms of commercial risk in the Northern Territory example, this PPA was very much a novel approach to risk management. Rather than saying we're going to take on the risk of the renewable system ourselves, we're going to leave it to somebody that can do better, or can do better. In terms of what they observed, they said that in negotiating a PPA, it was a big deal because they first of all said, yes, we're going to do it, but they didn't really agree to how some of these things are going to be measured. What happens when the grid's not available? How do you agree on what the solar farm should have been able to generate? So some of these things rock up when you start negotiating these deals, and they said that it would have been much better if there was a template for some of these contractual decisions earlier, so that it wouldn't have resulted in delay of the project. It's interesting to note that some people in when they're talking more in the developing country context, they say don't go with these deemed energy clauses where you have to dispute how much energy could have been generated, because it just ends up being in a whole bunch of administrative costs. They just say, work out before you sign up to a PPA what you expect, how many times you expect the grid to be down, and then factor that into your costs as you go forward. That obviously has some problems as well, but it's interesting to see how the literature reflects on that. I've mentioned that it's a separate entity. I probably don't have time to go into all of that. Programmatic risks, this relates to the political and regulatory things. So because this was treated as very much 2 different processes where we had the diesel generators and the renewable energy coming in, the money for the renewable energy system came from very much a green funding account. So they weren't allowed to put any money towards new diesel generators. The whole of system impact might have been much better if they had have put in a smaller diesel generator and maybe a little bit less PV, for instance. It's just the matter of that approach has created some interesting insights as well, I think. Obviously in Australia, we've had this project would have attracted price for LGCs. It would have attracted money in terms of large generation certificates, but obviously, you know, that you're exposed to some of the risks in terms of federal government policy and the changes to the RET. Future grid integration wasn't a risk in this case. Interestingly, the other KPI, other than delivering services to the communities, is to have a minimum amount of durations and of interruptions and a minimum amount of frequency interruptions, which is essentially the SAIDI and safety measures. While I didn't get end user data in terms of how many interruptions they had, everyone there kind of agreed that they were getting better services than what they had before the renewable energy system. How much of that is due to the fact that they're using renewable energy and they don't have to rely on diesel supply? And how much of that is due to the fact that it's just very much a rebuilt system? Like they've kind of come in with a lot of engineering expertise to make this system work better. If you did that at all the other systems, you might have seen the same results. So it's difficult to attribute how much of the benefits was to this. The next case study is in Malaysia. And again, you might be thinking, well, Malaysia's developed, why are you talking about energy access there? Well, it's very much a tale of two parts. This is Malaysia with Kuala Lumpur and Peninsular Malaysia on the left, and then Malaysian Borneo on the east. About 2/3 of the land area is on the right, and about 1/3 of the population's on the right as well. So this is the GDP capital in the left, and very much rural areas on the right. Similarly, when you look at rural electrification over time, you see these changes. There's been a much larger ramp up in Sarawak and Sabah, the two states of Malaysian Borneo. So that's been obviously a lot more research interest for me is looking into Sabah. So coming across, now this is zooming in on that little section on the right. This is where the utilities installed PV diesel mini-grid systems. You can see there's quite a number of them. The approach for that is very much the Ministry for Rural Development, who are charged with electrifying the country, as well as a trust fund which is cross-subsidising from the Peninsular Malaysia. They use that money to build these subsidised mini-grids as well as on-grid projects as well, grid extension projects. Anyone to receive grid central connection within 7 years, so that was what I talked about before on the earlier net cash flow diagram. 7 years might not be so much if you're talking about renewable energy systems. In terms of minimum contribution, they specified that in terms of 70-30 or 50-50. Similarly to the US, similar to the Northern Territory, the end users pay the same rate as on the central grid. So it's a statewide tariff and not exactly cost reflective depending on what system's providing it. The Ministry of Rural Development, which is in the top there, is responsible for village selection, load assessment and dictating the RE percentage. SCSB, who's the utility, will review all that. They then pass it on to a system technical design onto the contractor, who is basically a project manager that pulls together the civil works, the electrical works, and the renewable energy system as well. They put all those people in the same room. They put together a design. Then it comes to construction, and we see that that process can take between 3 to 4 years, maybe more. Finally, there's commissioning. The contractor gives a 2-year warranty on this system, and the ongoing operation and maintenance is the responsibility of SESB. This is some of the system sizes that we talk about. So there's a range from, you look at the PV there, going from 15 down to a megawatt or 1.2 megawatts in Tanjung Labian. Large scale storage systems as well, a range of diesel generators, and we can see some of those on the right. Won't spend too much time on that because I'm about to go into one on detail. Pulau Bangi is one island that I showed in the first slide, or the first couple of slides. And the configuration here is very much a blended AC coupling, DC coupling approach. So if we come down, starting off here, we've got the diesel generators, 5 diesel generators, all AC coupled into the bus bar. An AC coupled PV plant. This is 3 times 250 kilowatts peak PV, so 750 kilowatts. Some DC coupled PV here as well with batteries, DC coupled system on this side as well, and then an AC coupled system down the line further down the distribution network, so once we get outside of the power station. The reason this is such a complex design is because there was a smaller hybrid system on the island beforehand. That was operated in 2009. That got upgraded when they realised the significant load growth that would happen, so this became a bit more complicated in its design. Running out of time, but this is Pulau Bangi, the load over 24 hours. This is when you add the solar onto that load in terms of energy contribution. The DC coupled solar, the diesel generators run overnight. And then the batteries, if the power generation's more than the load, then the batteries will be charging. So a blue section above the dotted line is charging batteries. A blue section below the bottom line is the batteries feeding the load. And battery state of charge over time. This is when you add the irradiance onto the system. This is a pretty good day where you can see that PV profile is very much following irradiance. On the right, you can see a bad day where, for whatever reason, first of all, we found this issue with battery state of charge wasn't accurately reflecting the battery state of charge. The way we identified that it was actually an issue with the data signal rather than the actual battery state of charge was that if you look on the right there, the chart here, we've got we could produce a lot more solar than what's being generated, but you see this curve here is quite reflective of a float charge in sealed lead acid batteries, where the voltage stays the same but current gradually diminishes as the batteries fill up. So pretty confident that this battery state of charge indicator is wrong. However, nobody's looking at this data at the moment. The utility doesn't know that this data is wrong. The contractor doesn't know that this data is, whether the data is wrong or right. The utility doesn't have access to the data at all to operate how their systems are. So this creates a whole bunch of issues in terms of how they accurately commissioning the systems when these sort of things prop up. So obviously some performance monitoring could increase the accuracy and improve the handover process. We did a whole lot of surveys as well in terms of what people use electricity for in the bottom graph there, as well as what people were spending their money on in the non-connected households, those without the electricity grid. So they were using either personal generator sets or had like incandescent candles, or had candles such as the kerosene one in the bottom picture there. What this graph on the top shows is that the poorest people are still paying the most for electricity on the island. They haven't been connected yet, and this is pretty reflective of a lot of countries in the world where the expenditure on kerosene or the expenditure on personal diesel generators is quite high relative to what happens when you connect a household into the grid. Mind you, that's subsidised, but we'll talk about that. The performance of the system was quite low on Pulau Bangi because of this state of charge error. So the system thought that the batteries were low, so it was running the diesel generators more, and as I showed, foregoing a substantial amount of PV generation, which is a problem. There was no connectivity from the central Sabah utility, who couldn't monitor the systems. Obviously that creates a significant risk when you consider the size of these things. The end users reported outage durations quite low, 1 hour to 3 hours per week. So relative to what they had before, they were all very happy. 85% is pretty good. You wouldn't get that in Sabah, the capital city, because they've all got issues with SESB. They had a lot of issues attracting skilled staff to go out there and work on these systems in the first place, and they still have trouble retaining them there. I've also found that there's a bit of a gap in terms of the utility being able to, even if they did have access to data, would they be able to do the analysis that's needed to accurately monitor these systems. In terms of how the risk profile lays out between the government ministry, the utility and the contractor, we've got quite a lot of burden on the utility at the end, who didn't have too much involvement at the start of the project. So that's obviously one of the challenges that we're talking about. How can we better either put in a longer warranty from the contractor or incentivise them through a PPA to provide better service supports, because they're the experts in designing the system and they understand how the system works. So how can we better get them involved later on in the project? Finally, programmatic risk. There was a very poor coordination between government ministerial programs. There was these utility systems that were going in, school systems that were going in the same village, and then down the road there'd be community mini-grids as well, and there could have been some economies of scale. The last one, there's geopolitical, population and military influences, and one of the sites actually got invaded by a small sultanate of militants from the Philippines. That resulted in a significant load loss in the community, and then later a huge growth when the military moved in and set up shop as a base to stop it happening again. So these are sort of the issues that sometimes come up in these less stable areas than what we see in Australia. Spent a whole bunch of time putting together performance metrics. So moving on to how can we improve things. We've put together these based on demand side, system performance, etc. What I'll do now, rather than all the slides that I had canvassed, I might just skip through and show you some of the results. Peak sunshine hours at Tea Tree was quite good, as you'd expect. What we see in terms of when we compare all these factors between each one of the sites, the real good metrics in terms of assessing how much PV yield you're getting is relative PV yield. So this is a factor saying how much energy did you actually produce divided by how much energy could you produce based on your peak sunshine hours and the capacity of your system. So we see that the control errors that we had at Pulau Bangi, where they're running those diesel generators even when the batteries were fully charged, that's creating some issues and severe loss in terms of this is creating opportunity for a lot of improvement. And same at Tanjung Labian, which was the other site. Northern Territory, those figures are pretty good. You can see the capacity factors there are very good by world standards, but that's just as reflective of peak sunlight hours. Just run through all of these at once. There's a lot of challenges in hybrid systems for risk management. You're essentially custom designing 3 different components to fit a particular load. If that load changes, then you might have built something that's hard to maintain in the longer term. Diesel generators do this a lot easier, but it's one of the challenges that we just have to face up to and admit that there's a lot more demand. There needs to be a lot more focus on demand at the beginning and forecasting those things. Alternatively, limiting demand is another option. One of the major findings is, obviously that's a deal breaker. At the moment, the utilities not able to monitor their equipment, and that's a significant problem. As I mentioned before, there's a high dependence on the contractor, which is an issue. In both cases, there's still significant subsidies for the end users. What we could do to attract more investment from what we need in terms of development banks and private investors is having more cost-reflective tariffs. While that means that generally that's going to be higher cost to the end users, there's alternatives that you can use in terms of demand management, significant advantages in storage and the cost of storage and distributed energy as well. Finally, on the recommendations, avoiding this tragedy of the commons approach. I've talked to a lot of mini-grid suppliers and developers, and they're very reluctant to share data about systems, and this is one of the issues, is that they see that as intellectual property, but at the same time those investors are actually looking for people to demonstrate that these projects can work. And at the moment, by not sharing some of these lessons, I think we're suffering a little bit, or the developers and practitioners are suffering a little bit. In terms of how I'm mitigating risk in this process, you had the initial project lifecycle and all that uncertainty in terms of performance. What I recommend is these reviews, but also using what we've learnt through modelling and performance measures in the process to take a bit more of the reins in terms of how these projects are going to operate over 20 years. And in doing so, we can really reduce the uncertainty. I'll finish with a quote. Uncertainty is an uncomfortable position, but certainty is an absurd one. That just reflects back that while we don't really like talking about risk, it makes sense to admit that there is uncertainty, and you should be very sceptical if people are absolutely certain of a particular result. It's absolutely fundamental to good decision making to have a risk-benefit analysis. I'm working towards these guidelines for improved modelling, which is what the thesis is about. And I think that we've definitely got a role to play as academics to offer some value to the case study partners. Just finishing, I think we've got a large role. Minigrids have still got a large role to play. They really need to prove their mustard through this data analysis that I've been demonstrating. The Northern Territory and Malaysia have managed to pull it off and shown that these systems are technically possible but also effective. So that can kind of represent something that can be taken to developing countries as well. Just like to finish on acknowledgement, because I've had so much help both from the supervisors as well as all the people that I've met in the travels. It wouldn't have been possible without all those people. So too many to name, but definitely Dow Aaron and City in Malaysian Borneo was a big help in terms of getting me access to the data and getting us out to sites and things. So it's thanks to them that this research was possible. That concludes my presentation. If there's any questions, please jump in.
James, certainly covered a lot of ground there, but I think you've managed to leave enough time for a few questions, so do you want to take the question?
Alistair Sproul.
James, thanks very much for your talk, very interesting. You mentioned subsidies along the way. I'm just wondering if you could give us a little bit of a rundown on your view, because I mean, diesel prices are now sort of historically low. What sort of impact is that having on these sorts of risk on these systems?
Yeah, I mean, the diesel fluctuations, I've had to rewrite that chapter of my thesis where it's got all the projections of diesel going up and then showed the uncertainty now of that changing. The issue really comes down to a lot of these subsidies. I mean, with the COP agreement, there was this thing going around about reducing subsidies across the board, and that was very encouraging. But it's just so hard for political institutions when they're on the ground to actually make those changes because it's so unpopular. When I was in Jakarta, we saw significant protests and stuff when he tried to change that. But it's a huge problem. I'm not sure there's a real easy solution. As I mentioned, there's some ways that you can reduce tariffs once you have better demand management or storage options on site. But yeah, I mean, it's not an easy fix at the moment. And that's one of the things that's skewing a lot of the investment towards on-grid things, as you well know. I'm sure. Yeah.
I'm not very familiar with the demographics of Kalkarinji, but the peak load was during the day, and whereas compared to Pulau Bangi, it represented a more sort of residential profile suburb. So depending on these different load profiles, was one sort of more preferable for a microgrid with a PV retrofit, and yeah.
Yeah, absolutely. I mean, as you can probably imagine, if you've got the peak on the day, that matches well for reducing demand. So a lot of electricity investment is about that peak demand point. And if you've got air conditioners, so the reason there's a difference between those two sites, living standards in Kalkarinji, while it's still Australia's poorest of the poor, in indigenous communities there's a lot of air conditioners and a lot of appliances that are refrigerators and things like that. We don't have that yet in Pulau Bangi. So it's people, it's really just lighting, a few cooking appliances, television. People don't have the investment to put up front to put in air conditioners, but it's very easy to do the maths and say if you can reduce your peak consumption, how much you're going to save, and PV makes a lot more sense in that case. And you don't even need that much storage as you can derive, because you don't need to shift that load profile throughout time.
One more question, Andrew?
Yeah, that as you mentioned that there is a load profile in the Kalkarinji, there is in the daytime and in the Malaysia in the night time. Does it make any difference for the financial perspective of the power plant? How it is? Did you see some financial performance as well, that how it?
Yeah, so if you take the view that it has to be renewable energy that serves that load and you're only using PV, then you need batteries to meet that load at night. So that significantly blows out the cost of these systems, because not only do you have the high capital cost of the batteries, but you have a lot more losses induced as you pass the power in and out of those. So yeah, I mean, it's much harder to meet a peak demand at night, but the number of households that are on Pulau Bangi are a lot higher than what's in Kalkarinji. So as those people get, as electricity's just arrived there, we're expecting much more load growth. At the moment, it's something huge, like 4% per month. So it's going to settle eventually, but at the moment there's still distribution lines being run out into new villages. So that's one of the hard things in terms of estimating the load at the moment. This might not be reflective of the profile in a year's time or 2 years' time, and that's the challenge.
Last question.
So okay, we've got a technology which is seen as playing such a vital role, but so far is just really struggling to achieve takeoff, so to speak. We used to hear similar things about solar home systems, you know. Here was a promising technology that just never took off, but then it did in certainly some countries. What do you think your work sort of highlights about the differences between solar home systems and mini-grid systems, which meant one has kind of finally achieved programmatic and finance success, whereas the other hasn't?
I think definitely solar home systems, if you talk to the end user, are great as a stopgap measure, but they still all want the grid. And the advantage that mini-grids offer, or could offer in the future, is very much that surplus supply, as what we expect. There's a lot, decentralised solutions as opposed to grid connect solutions offer a lot of advantages in terms of they can be demand side driven, and that's one thing that is really important in terms of keeping the whole cost of an electricity infrastructure down. So they both have advantages, but I think I still back mini-grids in terms of they're more satisfying to the end user, but they also offer productive use applications. So people can actually dig out of poverty using, they've got enough energy to drive businesses or industrial processes and agriculture, which really improves livelihoods. Whereas solar home systems, while they're great, they have some limitations in terms of capacity. So in terms of future scale, the more these products get cheaper, I think mini-grids will come in to their own as well. Solar homes as well, like they're only going to get more and more, but yeah, we'll leave it at that.
Okay, thanks James.
Cheers.